is, you have to leave. Some of you might have to leave. The key is on Monday, I'll start where I left off and repeat it. So some people will get it twice, and it's nice if you can stay, okay? Because if you at least see it the first time, when you're over this period, because the test is a week from today. So no matter what, coming into next Monday, you want to almost be prepared to be able to take the test as much as possible. So 17, 18, 19, and as much of 20 as you can get, even if you leave. So that on Monday, all you will have to do is try to get that last part. But the thing is, the last part of chapter 20 has to do with this integration, which is sort of the critical thinking involved. So if you can stay today and at least see it for the first time, it will be to your advantage. If not, again, I'm going to be there at 4 o'clock on Monday. I was here today. It's 4 o'clock as well. I mean, I realize people have work and stuff, but this is it. Okay? You know, this is the time where if you're sort of struggling, it's like, I mean, I've taught this many years, sort of, get a divorce, call in sick, okay? Forget anatomy if you're in that. Who cares about anatomy? You have a chance, okay? This lab test everyone should have done well on, okay? It was almost, it was a pretty easy one. That's 60 points. And this test, everyone can do better on. Almost everyone does better than the cardiac, but it's intense, okay? So get into it, enjoy it, love it, and that's going to help you out. I promise you, okay? I promise no matter what, you're going to love this stuff. But it's a lot we're going to do today. So we're going to do it all today, and we'll basically do it all on Monday as well. The test is a week from today. And then, don't think about physiology for a week. Eat turkey. Enjoy the tryptophan, okay? Don't even think about, but every time you go to the bathroom, I promise you're going to be thinking of this, okay? So we're doing chapter 20. Now, when it comes down to it for 19, okay, I'll just sort of say it. I put it on the email. The idea of 19 is basically sort of, and I'm not going to really put much thing here, we really just dealt with up to here. We basically talked about everything controlling filtration and GFR, and the proximal tubule. Because the proximal tubule was what? Bulk reabsorption. And even the little details you don't really have to worry too much about, because I have details in this chapter. You have to remember that most of the water and most of the salt and all of the glucose and all of the amino acids under normal conditions are reabsorbed here. Okay? Bulk reabsorption. And that's what I want us to remember. So when you review, you're reviewing GFR and the three forces and local controls, and just sort of revise or remember all the stuff that's being absorbed or bulk reabsorption. And that's chapter 19. Chapter 20 is this, showing you how every other part's going to work. Every one of these segments are going to do something different. So, again, you're going to really see, osmolarity at work again. You're already seeing it sort of applying to things. Now, I just put this up here for a second, even though it's not on your handout right now, because here is sort of the money slide, so to speak. That at the end of this chapter, this is when we do this. That's why even if you leave today, you don't make it to the end, all of this of how to integrate systems, like going through examples or on the PowerPoint, literally what you're going to be able to do, this is a money-back guarantee, okay? After 5 weeks from now, we're going to be able to basically show you how the kidney is applying all these things. So blood pressure, acidosis, alkalosis, potassium levels, and the respiratory system. Basically, we're going to integrate all of those. So we can start with any of these, and you're going to tell me what happens in the other three. Just like last time we talked about if you inhibit alpha, you saw beta react, beta, we played 2 plates. You're going to be able to, all of you, every one of you in this room, will be able to say, if we start with high blood pressure, what does that do to this, and this, and this? Or if we start with low potassium, what does that do to this? It's not a memorization thing. You will be able to play all 4 plates, I promise. But that's at the end of the chapter, so we've got to make it there. But I just put that slide. So, again, you're not memorizing this, but when we step back a second, okay, before we get to the specific, we step back, and we already realize sort of that the kidney is going to work with what we just learned in the last section, the cardiovascular system. And it sort of should make sense to us if you look at this. We're not memorizing this whole thing. But we said when we had low blood pressure, okay, the cardiovascular system responded by that whole back page, right? Bell receptors, okay, very quick response. Well, what is the kidney going to do? The kidney is going to respond for low blood pressure to conserve water. And so we're going to show you how, but if you have low blood pressure, we don't want to pee out all that water, do we? We want to reabsorb water, and we're going to show you how it does it. So it's slower than baroreceptor response, but they're working together. Because remember, it's not like the kidney, the blood goes through once a day. It goes through 60 times a day. We have 180 liters of fluid, and we only have 3 liters of plasma going through the kidney. So when we're talking about conserving water, or the opposite, if we have high blood pressure, to getting rid of water, this is occurring. Okay, not as fast as the baroreceptor, but this is a lot of blood flow. So we are going to be constantly doing that throughout the day. It's not like it's just once a day. Okay, that's why the volume of fluid through the kidney is so important. But basically, it's the same idea. If our blood pressure is high, then cardiovascular system is going to respond by doing the opposite of what we had on that sheet. And the kidney is going to excrete salt and water. Why is it going to excrete salt?
Because it brings the water.
Water flows to where the salt goes, right? So, if the more salt we keep here, instead of reabsorbing, the more water, the more urine. And if you have high blood pressure, you're getting rid of salt and water. And remember, if you have high blood pressure, you want to be on a high salt diet. No, because it attracts water. So that's that idea. This is why it's osmoregulation. We really care about sort of where water is and where all these ions are. So, but that's just sort of a preview. Yeah, I like this picture. What can I say? But you're not memorizing. You're not memorizing numbers here. And so it's just to sort of get the whole idea that the whole course is about from day one homeostasis, right? We did it. We keep doing it. This is water homeostasis we're talking about as far as the kidney goes. So you're not memorizing these numbers, but here is sort of this idea of where we're getting the water in, and again, we're controlling about how much most of the water that we're then losing will be in the form of urine. Not much in the feces, and sweat, unless you're exercising, will change this, right? So there's a water balance, so nothing big. Here's one more slide of not memorizing. I'm not going to make you draw like a beer mug or anything like that. It's just visual. So, but then we're going to get to the real stuff. So visually, it's just I just sort of like it. GFR again is sort of this control that we control the flow rate. We talked about how last chapter. And so if you have a high blood volume and blood pressure, we're going to excrete more. If you have lower, we're going to, it says conserve, but we want to keep using the word reabsorb water. It can't make water, but it can conserve it, okay, and reabsorb it. If blood pressure drops too much, we're going to shut flow off to the kidney to make sure we have enough blood pressure. And that's all that's saying. So it's just sort of a preview picture. Now, okay, here comes, and that's actually, we'll actually put this, well, no, we'll actually just put the bottom here. Again, this is the loop of Henle. I'm just going to put Henle up here. This is the distal tubule. And, of course, this is the collecting duct. That's going to be a star today. Now, what we're going to see, we're going to play with osmolarity, salt concentrations, but at the end of the collecting duct, the urine can be anywhere between 50 milliosmol all the way up to 1,200 milliosmol. So this is very dilute. This is very concentrated. So if you think about it, if you're, let's say, dehydrated, or you have low blood pressure, which side are we going to go on? Are we going to want 50 or 1,200? You want to reabsorb water and make this concentrated. So we're going to show you how. That if you need water, we're not going to let all that water out. This is very dilute. This is concentrated. We're going to have a small volume of concentrated. We're going to reabsorb water. But we can go anywhere between 50 and 1,200. But how? Okay, and it kind of says up there too. If you have a lot of water, we'll throw out a lot of dilute urine. But if we don't have a lot, we're going to basically reabsorb it and concentrate it. So here's how. Here comes the magic. And I put this slide up. These are old slides, so it's not in your handout necessarily, to remind us of when we talked about, this is an exact slide from 19, when we talked about the nephrons, we saw that 80% of them, when we looked at the loop of Henle, didn't extend that much deep into the medulla. But 20% did, these juxtamedullary ones. And these we're calling the long loops of Henle. This 20% is responsible for being able to produce dilute to very concentrated urine. And we're going to show you how. These are the guys. That's why I put this picture back up. So all of these are involved in the other functions, but these 20% with these long loops are going to basically be involved in concentrating this urine. Now, I put this up here. You're not going to memorize that, as a thing, but here's where I put this. Here's my buddy Stu. Okay, you know my high recommendations of Stu Matz. When I was a kidney virgin, okay, this was a couple years ago. Okay, I was a kidney virgin. I didn't know about the kidney, and basically I came into Stu's class all like, okay, what am I going to learn today? And he put that up on the board. The long loops of Henle create a vertical osmotic gradient that the collecting ducts use to create more or less concentrated urine. And I'm writing this down, like, okay, I don't know what that means, but I'm writing it down. And by the end of the lecture, I'm like, wow, yeah, that they're actually doing that. And so I put that up here, but that's what we're basically going to show. I'm going to show you how, piece by piece. We're going to show you how this long loop of Henle, okay, so we're talking about the long loops, are going to create what we're seeing here, a vertical osmotic gradient. So vertical is up and down, and osmotic is how much salt. So we're on the outside, around this interstitial fluid, we're going to show you we're going to have a lot of salt at the bottom, like 1200 milliosmol, and then less, and less, and less. And so we're about to show you how this is going to create this long loop of Henle. Then we're going to show you how this gradient is all the way around, even though it's not showing the numbers. The collecting duct is then going to use that gradient to make more or less concentrated urine. So here is the magic. We're going to have to show you what's happening in each segment here. Okay? And then when we go back to that, to that quote, you're going to actually see what makes some sense. I want to show this picture. I put this on the PowerPoint only, just for visualization. And because when we show this, you're kind of like, well, where is this in the kidney? What does that really mean? If you just look at this, when we're talking about a vertical osmotic gradient, we're saying that deeper in the medulla, that's where the gradient is, right? 1200, 900, 600. That's when we're looking at this, is what we're saying. So I thought this was sort of a useful picture, because I think it's really hard when you're looking at that square one. So we're looking at the deeper we are, this is where it's going to drain out, into the renal pelvis, etc. The deeper we are, that's the deep gradients here. 1200, 900, 600, and then 300 again is isoosmotic.
So just trying to bring this all back, like 1200 osmoles mean, and then a regular cell is 300, it's going to go to where the party is?
Well, we don't know about parties yet. But yeah, this looks like it's going to attract water big time, doesn't it? Okay, and so does this. So we're not in cells here, because now we have tubules, and outside outside tubules we have salt. But it's going to be the same idea of where water is going to go from here to here or here. So it is that same concept. That's why it's osmoregulation. Which one? Our phone, this guy?
Yeah, it's not on the PowerPoint.
It is on the PowerPoint. Yeah, if you print out PowerPoints too early, don't print them out too early. I forgot when I put that on, but it's on one of them. You can take a picture of it. That's fine.
Yeah, I did.
Okay. Okay, are you ready? Yes. So follow me again. The way to do this is we're going to do a segment at a time, and you want to just see what's happening in each segment, because we've already done this. And let's follow osmolarity. So we have 300 milliosmoles, sort of, the blood. The filtrate comes in at 300. Even after all this bulk reabsorption, the top of the loop of Henle, this is going to be descending, is 300. Okay? And we already said bulk reabsorption. Now, let's look exactly what's going to happen as we descend. And what's going to happen is we are going to reabsorb water. And so you have this, that means that you're putting it both ways. We're reabsorbing. Remember, anytime we're going from what got into this back into the body, it's reabsorption. And so, we're just kind of putting it out here. We're reabsorbing water, as it says sort of here too. The key with this, and if you look up a second, we're saying water, and you can think of it a couple ways. You're reabsorbing it. Let me go back to this. you're reabsorbing it here, but what's not shown is we also have these paratubular capillaries which are sucking it up too back to the body. Okay, they just don't show it. So we have sort of the interstitial fluid surrounding the tubules, and you'll see other pictures, the book doesn't have it. We also have these blood vessels which are picking up that water and stuff. But right now the key is this. If you just look at this, you're this descending loop, we're reabsorbing water, okay? But we're not doing anything with the salt. So if you think about it, if you have, this is like how much salt is there. If you have some salt water and you're getting rid of the water, you're evaporating the water, what's happening to the concentration? Does it increase, right? We all agree. And that's what's happening. And as we do that and descend deeper and deeper, at the very bottom of the loop of Henle, it's 1200 milliosmol. So very, very concentrated. So as we descend this is the descending loop, we are absorbing water, salt staying there and becoming more concentrated. And that's what's happening on the descending loop of Henle. Okay? And again, I have words on the PowerPoint. Water is being absorbed, no salt, it's concentrated. Okay? Are we good here? We see how we got here. Now, the ascending loop, it doesn't look the same, does it? It looks like, oh, this is just a tube. Does this look like this? No. It's going to do a completely different thing. What the ascending loop is going to do is reabsorb salts. Sodium, chloride, potassium. Okay, and it goes, both ways. We're reabsorbing salts back into, again, right now, this interstitial fluid surrounding it. We're reabsorbing salts, okay? So, and we're going to show you, you don't have to know the mechanism, but we're pumping it out, okay? I mean, we're using ATP. We're pumping out all this salt out here. Sodium, chloride, okay? And you're H2O in here, right? And you're seeing all those ions, and what do you want to do?
Come to the party.
Guess what? No invitation. This is the key. This is the key. That on the ascending loop, okay, we're looking at the ascending loop up here, you have no water pores, which are called aquaporins. And we don't even usually talk about this when we're talking about water. Water, we'll actually see this, actually needs these pores normally to go through. There are no aquaporins, which means water cannot leave. Even though there's a great osmotic pressure out there, water can't leave. So each of these segments, we're seeing what happens and if water can leave or not. Here, water can always leave. Here, water can always leave, like we've been saying. But the ascending limb of the loop of Henle, water can't follow because there are no aquaporins. But we are pumping out salts. So think now right about what's happening inside here. If we are pumping out salts and water is not following, water stays in here, what is happening to the concentration inside? It's getting smaller, less, and here's the key. If you go to the top, okay, it's only 100. So if you think about this, remember the osmolarity means salt. You start off with 300, you end up with 100. That means, what have we done with the salt? Each time it goes through, we're putting salt out here, right? 300 in one pass, we're putting salt. Another pass, more salt. And I'm going to show you sort of a bottom line here. Can you start to see that if we're putting out an excess of salt, we're building some sort of high osmosis out here, okay? Because salt means osmosis. So each time we're going through, we're pumping out salt, and we're basically creating this osmotic force. Can everybody see that? Again, let me say that one more time, and then I'll say one more thing. So two things happening. Remember, and this is we're gonna show you it's going to be a vertical osmotic gradient. I'm going to just make you like an easy line versus how complicated it is. But the bottom line is that this is the long loop of Henle. It's going to create this osmotic gradient by the following way. On the descending limb, we're reabsorbing water only. The filter is becoming more concentrated up to 1200. On the ascending limb, and I'll show you a picture, we're pumping out salt from this filter back into this matrix here, okay? Creating all this osmotic force. As we're doing that, water can never follow. It cannot follow because there are no aquaporins, unlike anything we've talked about so far in the course. And so because of that, the filter is becoming more and more dilute. At the top, it's actually 100. So that each time we pass, we put out in excess of salt. Now, the key is, why is it vertical? Why do we have it that you see we've created osmosis out here, an osmotic force, but why is it ends up being vertical? The simple answer is you don't have to know for the test, okay? But I did put I put a slide on this, and there's actually a video clip. Let me just show you this. By the way, let me show you this because you don't have to know this specifically. The idea of the ascending limb, it's showing you, here's the interstitial fluid, here's the inside. It's showing you these different transporters. We need a lot of energy that we're going to then transport sodium, potassium chloride out. And again, water can't follow. But you don't need to know, you don't need to know this. I need a picture of transporters. You see that we've done transporters before. Just wanted to show this. But what I put on this that you don't need to know, but for some people, they can't deal with me saying this creates a vertical osmotic gradient. You get the idea of salt, but why vertical? That if you follow this, it's called counter-current multiplication. All it's doing when you follow this figure is after each pass, as it's accumulating more and more salt out there, it ends up basically, equilibrating in each time and then ending up creating this vertical gradient. The bottom line is, again, you don't need to know this. But for people that just can't deal with it, because I'm basically skipping of how it forms vertical, you can look at it, and there's even a video clip and some YouTubes online. Not tested, okay? Everyone see that. You don't have to be tested. All you're going to have to know is that the long loop of Henle is going to, and the word is key here. So let's put it again. The long loop of Henle creates. Underline creates this vertical osmotic gradient. So by doing something different, we're reabsorbing water on the downside and salt on the upswing here, and basically depositing salt. We are creating this vertical osmotic gradient. Create. Okay, once it's created. Okay, we've got it created, and we have it here. Well, we've got an issue here. Okay, we have more fluid going through there. Do we want the water now to dilute out the gradient? Do we want this, because we've got a gradient. Now if we just have water go there, what's going to happen to the gradient? It goes away. We need something to save us. Here's the savior for us. It's called the vasorecta. And this is a crazy, complicated figure. You look at this thing, don't freak out, okay? Take a drink, I'm going to take a drink. Because it's really, it's not going to be as complicated as that. But the key word is this. I'll even write it here, because you don't want to get confused on the test. And we're going to show you how. The long loop of Henle creates this gradient by doing the opposite on both those sides. But to maintain it, I put it in red, because you know my questions, and they're tricky. Those words, bring like 10 highlighters, okay? Underline key words, create versus maintain, decrease versus increase, so you don't mess that up on the test. But the idea of what we're going to show you is the vasorecta doesn't create it, but it's going to maintain it, and I'm going to show you how. So it maintains the VOG. I don't want to write vertical osmotic gradient. Now this is how. So let's follow this. So this is amazingly cool in itself. So it's called counter-current exchange. The vasorecta, this is just specialized peritubular capillaries. Remember, we have all these capillaries running next to these nephrons. We've got 1 million nephrons and millions of these, and so they're all over the place. But look at this. Okay, this was the flow, and this is what we talked about, right? The descending limb, we're reabsorbing water. The filter's becoming more concentrated. On the ascending limb, we're pumping out salt. Water can't follow, and it's becoming more dilute. But check this out now. We're going to have vasorecta, which is from the blood. It's running counter-current. This is the flow of the nephron. This is running the opposite way. And so look at what it's going to do. And we'll start over here. There's so much salt here. This is high concentration. Salt is going to basically, by high to low, is going to enter the blood here, enter the vasorecta. Okay, so don't worry about this guy right here. Salt's going to enter. And as it does, what's happening to the concentration of salt within the vasorecta?
It's increasing.
Up to 1,200. So in fact, this is picking up the salt. We already established that we don't want the gradient to be messed up now. This is still pumping out salt, but it's picking it up. Now on the upswing, we were basically, remember, water was being pumped out here or reabsorbed here. And when water looks at parties, what does it see here? Party back to the body. It's a moving party. And so the idea of this is, it's going to suck up the water. Instead of having the water dilute out the gradient, the vasa recta sucks it up. And what's nice is, you don't want the blood to be some weird osmolarity. You end up basically having the same osmolarity that it came with back to the body. So it picks up salt on the way down because it's running counter current, and then that's used to basically suck up the water so that we're not going to dilute out the gradient. That maintains the gradient. We establish it by doing these two processes, but now the vasa recta, by running counter current, I usually like to V with that, is picking up salt to become concentrated, and then that high concentration, that party there, basically sucks out the water. So instead of the water just sort of filling up and messing up the gradient, it gets sucked up and put back to the body. It's got to run counter current. So don't worry about kind of all these arrows here. It's sort of complicated. But the idea is, it sort of makes sense if you follow it. It's going to pick up salt on the way down, that's running this way, and this is where we're pumping out salt, to become concentrated, and then that part of that osmotic pressure is going to suck that water up so that we're not diluting out this gradient. We want to keep that gradient out here for the collecting duct in a minute. So, again, yes, go ahead.
So sucks out water on the way down.
No,
right?
on the way up.
Oh, on the way
See,
up.
it's running,
Okay.
yeah, because it's running counter current. So it's picking up salt sort of on the way down, because it's running next to this, and then it will basically pick up the water as it runs up. It's running counter current. This is pumping out water, it pumps it up. Or it will, reabsorb it or absorb it. Okay? And again, the first time you see this, it's still like you're like amazed, right? You're like, now you know why I'm like up at night thinking about the kidney already. We haven't even talked about the next step of it, but it's crazy. Okay, and anybody that's done anatomy and already learned these parts, there's no way, we haven't even got to the punchline yet, that you really realize each segment is doing something different. And so right now, all we've done is to create the gradient and maintain it. And you know what's happening here and what's happening here now. Okay?
Is this only in the long loop of Henley, not the short one?
Yeah, exactly. Because the short ones, if you and that's why I actually like that picture. Let's just go back a second. This picture, where you can see kind of a combination of pictures. When you saw the other loop of Henleys, you see it didn't really extend any deeper. So they're really not. They're doing all the other functions of the nephron. The other 28 functions, but they're really not involved in establishing this concentration gradient. It's that 20% with the long loops because they extend deep here and do it. That's why it's from another book. It's a really good picture. Okay, now we get to the distal tubule and the collecting duct. I actually put this back up again because the whole idea was, if you go back to Stu's quote, it was this. The long loop of Henle creates the vertical osmotic gradient so that the collecting duct can use it to make more or less concentrated urine. So we're about to get to the punchline. Now first, and this is important, that the distal tubule, okay, the distal tubule, although the book doesn't say, basically is doing the same thing, most of it, as the ascending limb. So most of the distal tubule basically will pump out salt as well, okay? And as it does that, water can't follow it either.
So there's no aquaporins in the distal
Right,
tubule?
for most of it, until we get to the end here. So all of the ascending loop and most of the distal tubule. So that when we actually get to the top of the collecting duct, I don't care if you're dehydrated, overhydrated, or whatever, the top of all of our collecting ducts here, it's at 50. Very dilute, because we pumped out a little more salt. Okay? As we pump out salt, right, we're becoming more dilute, we pumped out a little more, so that at the top of the collecting duct, it's 50. What's going to come out is anywhere between 50 to 1200. 50, 60, 70, I mean, all those in between. So here's what happens in the collecting duct. So we remember this, okay? You have 50, which means there's a lot of water, right? Okay, now, the filtrate's coming down, and what's it seeing out there? So what does it want to do?
Go to the party.
Okay, this does have it, it's by invitation only. Okay, this can never go. This can go by invitation, and what I mean is it's under hormonal control. And so we're going to show you the hormonal control. So these don't have aquaporins inserted, but we're going to be under hormonal control to do it. And the hormone that's going to do it is ADH. Okay? So again, I put this back up again, just for fun. Again, remember the book, I've got the figures for the book, I can't help it. They put the top is at 100, but it's really already at 50. So they sort of skip that. So you kind of go on this. But we'll look at that picture right now, that without any hormones, because this is why we created this gradient. Without any hormones, basically the water cannot, there are no aquaporins inserted, so water can't go to the party, and so we're going to end up basically dilute urine. Again, for us it's 50, they put 100. Okay. But it's under hormonal control. And the hormone is, I think I put it next, is ADH. Also called vasopressin. You're going to have to know both names for it. ADH stands for anti-diuretic. Okay, diuretic makes you lose water, pee. This is going to be help to conserve water. Anytime you think ADH, because you got 3 letters here, you just keep saying ADH means water reabsorption. Anytime you need water, your ADH is going to go up. Okay, I mean that's the first thing that you got to just got. It's vasopressin too, but ADH, water reabsorption. We put it back to the body. So you know anytime we need it. If we have low blood pressure, if we're dehydrated, ADH is going to go up to reabsorb the water.
So we can conserve water.
So we conserve water. And for us, we keep on to use the word reabsorb because that's like the word, that we're going to basically, the water that's here, we're going to reabsorb it back in the body, which is, in another way, conserving water. But for us, you really want to get that idea of reabsorb. Because that's sort of an important concept. So we're going to reabsorb, and most of the water we're going to do, look here, it's at 50. If we need to reabsorb it, it's going to be right here in the collecting duct. The collecting duct, the cells of the collecting duct are sensitive to ADH. And that's where we're going to reabsorb water. What they're going to do, and then we'll show you sort of this other punchline of it, is we kind of get, let me just show this picture, a picture that you don't have to know the steps for. What it's going to do is, that, remember, it's called vasopressin as well, that when you release this hormone, the cells of the collecting duct are going to react to it, and the aquaporins are there in the middle, but they're not inserted. So ADH, or vasopressin, is going to cause them to be inserted, and then we can reabsorb the water. That's how it's going to work. That's how this collecting duct is going to be under hormonal control for the aquaporins. No ADH, no aquaporins. ADH, we're going to start doing it. Now, here's the key, and listen up to this one, because it's like, why did we create, how are we going to use this vertical osmotic gradient? So, the cells at the top of the collecting duct, like those guys, are the most sensitive to ADH.
The cells at the top of the collecting duct?
Right. So you see those are like the cells, right, supposed to be. These cells that have those aquaporins inside, but they're not they're not inserted yet, they are the most sensitive to ADH. Okay? So, and that's why we're going to be able to use this gradient. So that means if we just need a little water, so let's make a little ADH. Okay? Just some. The cells down here are not going to react to it. Only these cells are going to react, which means we're going to insert aquaporins here at the top. We're going to reabsorb water. And the key is, if we're doing this at the top, we come to an equilibrium. So that instead of 50 now, let's say we inserted aquaporin, we had some ADH, these cells reacted up here, we reabsorb water, now urine will come out at 300.
So ADH creates aquaporins?
It's over here. What it's going to do is, it's going to go to those cells, bind to it, cause the cells to insert the aquaporins they have sort of sitting in the middle here.
Okay.
Okay? The top of the ones are the most sensitive. So if we just need a little water, we'll just make a little ADH, we'll insert aquaporins at the top and absorb some water, and then we'll equilibrate to what's around it. Let's say it's 300. So we've concentrated our urine a little more. What if we need more water? We're going to do what? More ADH. Now these cells in the middle are sensitive enough to basically insert them. And now we're inserting aquaporins further down. We're reabsorbing more water. And what's happening now, okay, 600. Okay, so the more, this is why we created this vertical osmotic gradient, because now, because of the sensitivity, if we need a lot of water, okay, we're Bear Grylls with him in the desert, I don't know what we're doing out there, you're in the desert for 3 days, you're going to make the maximum amount of ADH you can. That will allow us to insert aquaporins all the way down the collecting duct. For us, the most that we can create is 1,200. So we absorb the maximum amount of water we have by inserting all these aquaporins, come to that equilibrium, and we'll have very concentrated 12 milliosmol urine. So because we've reabsorbed as much water as we can. Okay, we can't do more. If you were a desert lizard, and if any of you wants to be one, they actually can do this up to 3,600 because you really have to conserve water as a desert lizard. The most we can concentrate it, because we have to get rid of waste and toxins. Okay, so we have to actually have some. The most we can concentrate it is this. So and I'll answer your question. So again, let me just say one more time here before we'll answer more questions. Again, we created this vertical osmotic gradient, and you saw how. To basically, the collecting duct is using it to create more or less concentrated urine. The collecting duct is under hormonal control, mainly ADH. ADH means water reabsorption. So that the more water you need to reabsorb, so the more concentrated the urine, the more ADH you make. You start inserting aquaporins further and further down. You had a question? Or?
Yeah, I just forgot, like, we make ADH because our brain tells our kidney to make it, or?
No. In fact, let's go back to that. And don't worry, we're gonna deal with this a lot as we go too. So basically, we're going to talk exactly the conditions, like dehydration, all that. We're going to show you. Basically, the hypothalamus will make it, release it into the blood, and will affect the kidney here. Okay, so the kidney is not, well, we'll see indirectly maybe, but the kidney is not telling it to make it. It's going to be our body saying we need water, so that our brain makes ADH. ADH comes here and then starts inserting aquaporins. These are the sensitive cells to ADH.
And it's transmitting it, like through neuro.
Say that one more time.
I was just saying the brain's transmitting it into the blood and it's going to the kidney.
Yes, because it goes everywhere.
Right.
And so and we'll deal with, and if back in the beginning of the course we talked about nervous system and hormones controlling everything. So this is so interesting because it's kind of a link. But the idea is this: the hypothalamus will make it, but once it puts in the blood, it's like a hormone. Okay, basically. And so in this case, we'll talk about oxytocin at the very end of the course. The last slide of the course is like breastfeeding, which is really weird to end the course on that, but we'll talk about oxytocin. But in this case, we're talking about ADH. Okay, so ADH then will go again. Think about vasopressin, it's the same thing. When we need water, our brain's going to basically be signaled to produce ADH. ADH goes to the collecting duct, and depending upon the level, how much water we need, it's going to start inserting aquaporins further and further down. More and more water gets absorbed, the urine becomes more and more concentrated. And we have a range anywhere between 50 to 1,200. So remember back in last chapter I said magic? You know the magic now, or beginning to know the magic for the first time. And you see everything is doing something different. And when you review this, I'm going to take a drink because we're going to ask, we're going to keep on going in a minute, and then I'll answer questions too. But I just want to keep reminding you, when you're practicing this, what I recommend again is, of course, everyone has a whiteboard, right? I mean, I should get some kickback from whiteboard sales, right? I should just start bringing them in. But the idea is you draw all this and you and basically just make sure you realize what's happening in each segment, what's happening to salt and water, and again, you can see by the questions I actually put on the even the take home, because I thought you could read ahead. I'm asking, where can water always be reabsorbed? Where can water never be reabsorbed? And where is water controlled by hormones? And you can start to see every segment is different now.
So the more you descend the collecting duct, I guess more potential you have to have increased ADH.
It's kind of the other way around, right? The more ADH you make,
The lower you are on the
the lower, then these will start inserting aquaporins more and more. So these aren't that sensitive. If you just have a little ADH, these won't respond. Only these will. So in order to get further down into this thing, you need more and more ADH. So that's why we sort of have this reverse, right? We create more concentration here, but more sensitivity up here. So a little ADH will only allow us to insert it at the top and basically concentrate the urine a little bit. The more ADH, the further down we can start inserting, concentrated more, and the most we can do is 1200, because that's the gradient we made. This created the gradient for the collecting duct used to make more or less concentrated urine. Do you see why StuMats is beautifully ingenious? Simple statement to put up there. By the end of this, you actually see it. Yes?
So, and this is brought in by the low blood pressure and
We're going to do that now, yeah. So we're going to actually show you, conditions now. Low blood pressure, high blood pressure, and osmolarities to actually integrate all this as well. This is sort of the mechanism, but let's show you how the body is actually using this. But before I do that, any questions on this? Are people starting, again, the first time you see it, you're just in amazement, like, wow. But so you can't quite get it, but everyone should be sort of getting it, yeah.
I think I can kind of answer my own question, but sometimes you have only a little bit of urine and say like it's dilute or it could be really concentrated. And I was just thinking if you reabsorb more, then you're going to have more concentrated, but that doesn't necessarily mean that you're going to have the less volume. It kind of depends on other.
It usually does.
Yeah, I mean, I guess it would. That's what I was wondering, because salts aren't. The bulk of it is the water. All you're doing is absorbing the water. And
you're going to see a real kind of concentrated urine. They usually will go pretty well together. Yes, ma'am.
Why is it more concentrated in the morning when you first wake up?
You have see. No, wait.
You know what I mean?
Yeah. No, I know what you mean. Well, you're sort of getting dehydrated during the night a little bit, but the idea too. It's interesting that you say that too, because you actually. Oh, this is sort of the reason. Like, do you want to pee in your bed? So what happens unless, and this is the idea for bedwetters, and I don't making fun of them because some of you might be bedwetters or might be soon after this course. But the idea is naturally we actually during the night increase ADH to reabsorb water so you don't actually pee. Okay, and so you are reabsorbing water during the night so that when you wake up and you start to go, you're going to have a concentrated urine. So, and that's why for bedwetters, one of the common things is you're not, and so if you're not conserving water, the water's continuing to go, and it's going into the bladder, and then it can, there's other things too, but it can cause it. That's the answer. Actually, know an answer to a question. Okay, good. Sometimes I'm like, I don't really know, Any other questions?
I'm confused why it's being more concentrated and we're allowing water to go in.
This is reabsorbed. This is where, and sometimes, what?
At the end of the connection.
At the end, yeah. I mean, the idea is, if we're reabsorbing water, okay, which is what we're doing. This is in effect. They have see the pictures aren't perfect here. Let me see a better one here because they don't show. Like all these vasa rectas and peritubular. There's like a million I'm running. That when we're saying we're reabsorbing water. It's being picked up by these blood vessels and put back to the body. So it is reabsorbing back to the body. And as you do that, again, what's happening inside is we're going to come to the equilibrium of the salt around it. And that's why we created a vertical osmotic gradient, right? So at the very beginning, if we only need a little water, we'll just put aquaporins here. Water will go back to the blood, but we're going to equilibrate to the osmotic gradient, like 400. Okay, if we need more water, more ADH, we'll start inserting aquaporins here, water's reabsorbed, and we equilibrate to the vertical osmotic gradient. That's why we need the vertical osmotic gradient, okay? If we just had 300 out here, we wouldn't be able to concentrate urine at all, or we'd only get to 300. By having this beautiful gradient here, and this different sensitivity, which is, again, kind of weird, that's how we're able to do it and control each step. Yes?
When the solution's concentrated at 1200 milliosmoles, do you call that hyperosmotic solution?
No, because, I don't know, some people might, but I mean, it's just because, remember, it's not like inside the cells. It's a very concentrated urine. Maybe some people might call it hyperosmotic solution, or I don't know.
I didn't know if that was something I needed to know.
No. I mean, but you see it is very, very, it's high osmolarity.
Okay.
But usually hypo is when we're actually looking in the body, around the cells, which we will.
Is water being absorbed too in the proximal?
Big time.
Yeah.
Bulk water reabsorption. And when you look back at the figure, like most 2/3 of the water gets absorbed there. See, this is sort of like we've got to do this heavy flow, 100 milliliters a day, because we've got to control all these things. We haven't even talked about them all. But the idea is, we want to get most of that right back. Okay? We want to make it so it's easy to get in. That's why we make this sort of non-selective. It's just like if you're small and not cells and protein, you're in. But most of the stuff we put right back. That's why that was bulk reabsorption. All of this is fine-tuning. Okay, and so we are going to reabsorb some more water and some more water here as well, but you know, the bulk of water is here. Always we can do this. Aquaporin's abundant. Aquaporin's abundant. Never, never hormonal control.
So if water can't get out in the ascending limb, why is there less salt?
There's because we're pumping out salt. That was what we were doing, right? We are pumping out salt, right? Where is that guy? With that transport, or we just put this, you know, ions being reabsorbed, that's salt, water's not, so it's becoming more dilute.
Okay.
That's why those are the two cycles.
What was your never, never again? Can you
Never, never.
Yeah.
The ascending limb and really most of the distal tubule can never reabsorb water. There are not aquaporins. I don't care how much ADH you put on them, throw on them, okay? Never, never hormonal control. Yes?
The vasta recta, like I know the paratubule and caspial, whatever, are like around the tubules, but are they everywhere where they're doing the reabsorption? Is the vasta recta, is that it's reabsorbing stuff too, but in a different way, going to mouth?
The thing is, and it's a great, I mean, you're not the only one who asked that too. Well, we see the problem with it is, let's just go to this. And actually the one they have, let me just show this one. Yeah, that one. You know, this is basically what to do. We've got a million of these things like going, you know, so we can't show that, but they're all like they're doing their thing, right? You have well, it's really only, I guess, 20% of them, but you got all these loops of handling and all these ones, so you can't really show that, but they're all doing it, basically. But sometimes it's confusing because it's like, whose vasorecta is this? And I mean, I understand the pictures really don't do justice.
So the main thing is that it's in the loop.
Yeah, the main thing is what it's doing, that the ones that are in the loop especially, that the idea, yeah, how it maintains it, by picking up salt, putting up the water back to the body, maintaining it. Nothing beyond that. One more hormone, and then we're going to put something together. I have one more hormone that we're going to talk about. Well, we have a couple more, but right now. Another hormone is going to work, and I'm going to sort of clear this up a bit. That if you look here, which is going to be, let's see if I show that picture here. If you look, and we'll kind of put this up here. If you look at the end of the distal tubule and the top of the collecting duct, there are cells called principal cells. And these cells are going to respond to the hormone aldosterone. Okay? So these respond to a hormone called aldosterone, which, we'll go back to this, it is made by the adrenal gland, specifically the cortex. And the last section of the course, we actually deal with hormones. The outside, again, we have this idea of cortical medulla. So the cortex of the adrenal gland makes aldosterone. And the cells which respond, we're fine-tuning things here, are going to be these principal cells located in this region here, the sort of interspersed. The end of the distal tubule, top of the collecting duct. It's sort of where I drew the circle. And what they do, this is really important, is when you think of ADH, you're thinking water reabsorption. When you think of aldosterone, it's going to fine-tune and basically cause sodium reabsorption. We're going to, again, going both ways, we're going to fine-tune and actually reabsorb into our body more sodium. And if you're reabsorbing sodium into your body, who's following?
Water.
Water's following. And even put that. H2O follows. We're going to show you on the next part how these work together. But the idea is we're fine-tuning things. So we know we've got salt coming back and salt coming back from those two segments, and this, and this. But here we're going to fine-tune it, and we're going to see it's under hormonal control. So all of this is hormonal control. ADH is collecting duct, the aldosterone, these principal cells located here. In this case, we're primarily reabsorbing sodium, but some water could follow that as well. So when you need salt and water, you want aldosterone as well. So let's make a chart here. And this is going to be making sense. Okay, it's a lot of stuff, but so far we're in good shape here. And we can repeat this over and over and over. You want to start doing that to really get it. But I'm going to write this. I'm going to write low BP. Okay, leave a space, and I'm going to put a couple things here. High BP.
Is this gonna be a huge chart?
No, what's? I
Do
don't
we
know.
need like a full page?
Yeah.
No, I don't know. It depends how big you write. I don't know what to say. I'm going to fill up right here. You might want to make it a full page. Okay, it's a good page. I don't care. Okay, low blood pressure, high blood pressure, low blood osmolarity. Okay, osmolarity or high osmolarity. Those are 4 conditions we're going to look at. And if you're doing this, leave a little space right here, like at the top here, actually all over. Leave a space and then start writing. And what I want to write in all of them are the following. I want to write ADH, and then ALD for aldosterone. ADH, ALD.
Is this after the space?
Yeah, because I'm going to put some stuff above it. But we're going to do this first. And then ADH for all of these. Because basically we want to show you, and you're going to be able to just easily figure it out, as long as you remember what we said over there, what these levels of these hormones are going to be in response to these conditions.
This is the essay question.
No.
Oh,
I'll tell you, the essay question I'm going to tell you in a minute. But this is going to be to answer a bunch of multiple choice that you will have, that you'll probably put this chart on next to it so you can answer those multiple choice. Okay? I'm going to tell you the essay question in a minute, the main essay question. So, okay, so basically I'm just saying these conditions are going to trigger this. And to figure this out, it's not going to be a memorizing chart, because all you have to think about, especially for these, this will be a little different, is what these things do, and if you need it, right? ADH means what to us? Water reabsorption. So if you need water, ADH goes up. Aldosterone means what?
Water and salt.
Right. Okay, so when you need that, it'll be. So if we just go this. If you have low blood pressure, okay, what's ADH going to do? Go up, because what do we want? Water reabsorption. ADH goes up, H2O gets reabsorbed, we can raise our blood pressure. How about aldosterone? Okay, aldosterone means what? Salt and water. Do we want salt and water? Sure. Both of those are going to be signaled. You have low blood pressure. We don't want the kidney to lose salt and water. What do we want? We want the salt and water to come back to our body to raise our blood pressure. Low blood pressure, and part of this we'll see the essay question, is going to trigger an increase in ADH, which is water reabsorption, an increase in aldosterone, which is sodium reabsorption, and of course, H2O reabsorption follows. So by putting salt and water back in our body, then we're going to help restore blood pressure, or attempt to restore blood pressure. Does that make sense? Does it? And you see, this is not like a weird chart. As long as you remember what these things do, common sense, right? We know what we need then. Low blood pressure, we need water and salt. So as long as you associate those, they go together. Most of the time, these things go together. So if you think about it, if you have high blood pressure, once you have this, obviously that's going to be the opposite. So under high blood pressure, we want less ADH and less aldosterone so that the salt and water stays in the tubules and goes out. So it will help lower the blood pressure.
So people that have high blood pressure, don't they take water pills?
Diuretics, and we'll show you, if you just hang with me, and I can tell you preview here, water pills in the sense of diuretics, okay? And diuretics are going to make you pee more. Guess what diuretics do? What are they going to end up creating in here? Okay, instead of reabsorbing salt, what if we block the reabsorption of salt? Salt is going to stay where?
Oh.
And who's following?
Water.
That's how all diuretics work. I gave you an extra sheet on diuretics, which you don't specifically have to know, but you'll see there are loop diuretics like Lasix that prevents or decreases reabsorption here. More salt stays, water follows. Why I say this is important, there's other ones that work here. Prevent reabsorption of salt here, salt stays here, water follows. There's aldosterone receptor inhibitors, which we'll talk about, that prevents this from reabsorbing salt. Salt stays here, water follows. All diuretics basically do is keep more salt in the filtrate, water comes with it, boom. Okay? So you understand diuretics just by osmosis, okay? And we'll revisit that again. Any questions about this? Do people see how you can reason both of these? Yes?
So I just had a quick question, right? Inquisitive statement. With the low blood pressure, why is salt and water making it low again? Like, how does that help, like, moving it?
We're putting it back in our body.
Right.
Okay? Well, if we have low blood pressure, if you put water back in the body, or less goes out, doesn't that make sense that blood pressure goes up? Blood pressure is blood volume.
Oh, okay.
So think of blood pressure. Think of it that way. Maybe I didn't say it that way, right? So blood pressure, or at least part of it, has to do with blood volume, and so you want more volume in. So that's the
I didn't know
idea.
if it was making that much of a difference, like.
No,
Yeah.
it's a good point, because I didn't, sometimes I will say it, but I'm not making that clear, because sometimes other things can cause blood pressure besides volume. But the idea is, if you have blood pressure for any reason, low blood pressure, your kidney is going to respond by trying to raise it by keeping the water and salt in to build up volume. Okay, and we're gonna revisit this for the essay question, because low blood pressure is sort of the deadly guy, right? High blood pressure is chronic. Low blood pressure, you can die, and this is going to be, we're going to tell you sort of the master control of this. Okay, and so, but let's do the low and high osmolarity. And to do that, I usually like to draw pictures so we don't mess it up. And remember, the inside of the cells are 300. So low osmolarity means outside the cell is less. High osmolarity means outside the cell is more. We'll just put numbers in. Okay? Now, again, let's look at this. If you have low osmolarity, okay, you have less outside. If we did nothing, which way is water going? Where's the party?
Inside the cell.
Inside the cell. That party thing works so well, it's not even funny. And then your cells might burst. That isn't good. In this case, if you have 330, if it's high osmolarity, we're going to dehydrate the cells. Okay. So now when you're doing these, you're basically asking questions. Everything that you're doing here is affecting the outside, and so you're asking, do I want water? Do I want salt? So if you have 270 out here, okay, versus that, do you want more water in there? Do you want to dilute this out more? So ADH needs to go. Okay. Do you want to add salt?
Yes.
Yes. Now, they're working in opposition. And I know somebody's going to say, hey, Mike, but water will follow. But hey, not yet. Not that much water is following. We don't want our cells to burst. It's worth putting more salt in to increase the concentration. So even though some water will follow, we'll correct the condition and then deal with all this stuff later. So again, everything's gets more complicated. But if you just think about the initial thing here, which is these are going to work. These normally work in conjunction, right? Same direction. But these are going to sort of temporarily cause them to be opposite. So we don't want water, but we do want salt to sort of get that back up. Okay. Same thing here. You've got a 330 out here. Do you want to dilute that out with some water? We do, right? Do you want to add any more salt? Okay? And so, and in fact, I don't know if I put it here. Let's see. I actually might have just taken it out totally. But there's charts in the book that have all this on it in something a very complicated way that you just simply don't need to know. Okay, and actually, again, I put this slide because this is what we're dealing with. So we're gonna fill this in, especially low blood pressure. That's going to be your essay question coming up next. Okay, how we control this. But here's sort of this idea of just incorporating these two hormones of what they're going to do under those conditions. This is an essay question, but I'm going to be saying you have blah, 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 and aldosterone goes up and that goes down. It's going to be one of those things where if you have that, you're going to find the right answer, okay? If you have low osmolarity, the right answer is going to be the one that has ADH going down and aldosterone going up. So it's a handy chart to put on. I left this blank because low and high blood pressure, there's the central hormones that are going to control it. And first of all, let me show you this, and we're going to do the essay question and that. The key is, we're going to memorize this pathway. It's called the renin-angiotensin-aldosterone pathway. Okay? And this is going to be the essay question. Literally just that flow chart.
Is that the low blood pressure?
That's low blood pressure.
Okay.
Okay? And the key with this will be, I'm going to put it up there and explain it, that under low blood pressure, remember, this is critical. We're going to produce, and we're going to show the kidney does it, renin. And so let's just put it up here for now to fill it in, and we'll go through this. And we're going to show you how. we're going to show you that renin is going to then, indirectly through this pathway, increase ADH and aldosterone just like we want. So I put renin up here, increase renin. And I'm going to show you how. But right now, just for a handy little chart, let's just put that.
You mean the renin pathway, right? Or just renin?
No, just renin. Because this is the simple guide just showing the hormone levels. Don't worry, we'll get to this. So just put increased renin, they fall together. Okay? Let me just, and we're going to come back to that because the next one's not the essay question. So, and we're going to show you this. We're going to show you that renin, after this pathway, is going to increase aldosterone, increase ADH, vasopressin, to do this, like we said. So, but we're going to know that happened. Okay. But before we do that, let's just fill in the other one. And you're not going to have to know this pathway. But the idea is if you have high blood pressure, okay, we have sensors in the atria that says we have high blood volume. Okay, so we're really relating pressure to volume now. If you have high blood volume, the atrial cells are going to produce a peptide called ANP, atrial natriuretic peptide, that is going to decrease these. Okay, and you're not going to have to know this pathway at all, but it's going to be a similar idea. So in this case, you want to just remember that high ANP, which is the atrial natriuretic peptide, it's going to cause a decrease in ADH, which is vasopressin, wherever it is, and a decrease in aldosterone, just like we have up here. So you don't need to know this chart. You don't need to know anything else that's on here. All you have to know is that high blood pressure, A and P goes up, and that's going to cause the decrease that we already figured out. And this chart's complete. And we're going to go back to your essay question.
So renin is the one that increases ADH and ALD?
Yes. So look at this thing, and I'm going to talk about it. So this is and I don't know if we're having another one. I'll see. This is the major essay question. Depending on my mood, I might make it 8 to 10 points. It just depends on how I feel. But so it'll be something like that. And it's literally reproducing this. But let's go through this process. So this is a major trigger process here, and we're going to follow each step. So it's called renin because we're going to talk about angiotensin, and that's pretty important. Here's ACE. Anybody hear of ACE inhibitors? Okay, we're going to see how they work. Okay, it's very cool. We haven't even got to the cool part. Okay, that's why it's like you've got to stay. I don't care what you got. Call in and all that. Just bring some pizza in. We've got another good hour of the coolest part. This is just the preview part, right? This is like some of the cool previews. You want to see the movie? The movie's coming, okay? The movie is coming. All right, it's crazy, okay? All right, so I guess sit down for this. So, follow this and see what you're going to have to know for the essay. So the liver, we're going to have to know like all this, like who makes what and sort of the idea of this. The liver is constantly making something called angiotensinogen. Do you think angiotensinogen is active?
No.
No. It's one of those zymogens, right? It's one of those inactive guys. If we're going to have low blood pressure and we want to react, we want everything ready to go. We don't want to have to say, please make some protein liver and bring it but we want to have it there. So it's always making angiotensinogen. That's going to remain active unless there's a trigger. The trigger is low blood pressure. And look who's involved. The granular cells of the kidney actually then, remember the kidney, the flow through it, it's monitoring blood pressure pretty well, right? Because you're flowing through it. It says, okay, blood pressure dropped. The granular cells, which are around those afferents, are going to produce a hormone. Remember how we formed the kidney? It's called renin. Okay? Now what renin does is converts angiotensinogen to the first form of the actual more active form, angiotensin, called angiotensin 1 or Ang1.
Renin converts what?
This guy to this.
Oh.
Angiotensinogen to angiotensin 1 or Ang1.
Which becomes active.
And it's active but not very active. Here's the key. This is when we talk about ACE inhibitors later today and on Monday, you'll see why it's so important. That the blood vessels, the cells in the blood vessels are always making an enzyme called angiotensin converting enzyme or ACE. So that if Ang1 is there, okay, it's going to convert it to the active guy Ang2, angiotensin 2. And that's the active guy that's going to do all this. That's why ACE inhibitors will sort of block this whole thing, and we'll see why they're being used. But that's the first few steps. Okay? Liver makes angiotensinogen, which is inactive unless it gets triggered. The trigger in this case of this pathway is low blood pressure, and it's the kidney, The granular cells produce renin, that converts it to Ang1, but then ACE, which is already in the blood, will convert it to the active form Ang2. Okay? Now, this part of it, you're not going to have to know, because Ang2 is going to go to the cardiovascular system and do everything that you drew on that page of your test. Help it. Okay? So we did that. We don't really want to put that on the test. You can put it on the test for fun, but I'm not going to want you to put this, or this, the cardiovascular response, because we already know the cardiovascular response. Okay? Let's look on this side though. Okay? It's going to go, this is circulating. It's going to go to the hypothalamus and increase vasopressin, which is ADH. Sorry, you've got to remember both of them, like we said. Okay? That means water reabsorption, and that means it's going to help, raise blood pressure. It's also going to the adrenal cortex. And adrenal cortex says what? More aldosterone. More aldosterone means sodium and water reabsorption, and now we can increase it. So we're trying to counteract low blood pressure by doing what we said, increase ADH, vasopressin, and aldosterone. Ang2 is going to help us do that. It's literally going to the two places that make it and cause it to make it. So, and then you don't have to put thirst, but it does, hypothalamus does trigger thirst, so we can actually restore volume as well. You don't have to put that. But everything else you have to put, including, you don't need, I don't want essays again, I mean, you can have it, but then I got 100 of these things. It'd be, if you put something very like this, it would be like, 10 points. So, let's just go through it again and see if it makes sense. So,
Is this the movie, by the way?
this is what?
Movie.
What movie?
Well, for staying, do you get what I'm saying? Like the big picture? You
This?
said previews and then movie is gonna happen?
This is not the movie.
Okay.
Well, this is, this is like a video short, okay? It's sort of a cool thing, but not the real thing coming
So
out.
is Ang going to the hypothalamus and adrenal cortex at the same time?
Yeah, because this is like hormones going through the blood. So boom, it's going to everywhere. But these are the active places to actually make the hormones.
Okay.
Okay? Does that make sense? So again, the liver is producing this zymogen, this inactive guy ready to go, so it's always throughout all the blood. But the trigger is low blood pressure. The kidney senses low blood pressure because all that blood is going through it, or filtering through it. So it says, okay, blood pressure is low here. The granular cells are going to make renin, and then comes the fun. Renin converts angiotensinogen. Okay. Again, I'm not totally big on spelling, but you've got to come pretty close. Okay. It can't be angiar or something like that. Okay. I've got to see that you put angiotensinogen pretty close, maybe a letter off. Renin converts it to Ang1, and yes, you can put Ang1. Okay. That's inactive. The blood vessel are going to produce ACE, which you can put, converting enzyme, to make Ang2. That Ang2 circulates through the body. It does all this we don't care about. We're not going to be listed on this. But in order to restore blood pressure, we want to increase volume. So it goes to both of these places to make more of this. It goes to the hypothalamus to increase ADH, which is vasopressin. That means more water reabsorbed. It's going to go to the adrenal cortex, produce more, cause more aldosterone to be released, which again, over here will cause more sodium and water to be reabsorbed. Again, that restores volume and salt. That's going to counteract and restore blood pressure. Very important, right? Blood pressure drops too low, you're dead. So this is a quick response. That's why we have all these things ready to go. We just need a trigger for the explosion, and the trigger is low blood pressure and the kidney. Okay? So this is sort of, the preview, but the sequels are coming.
I know a lot of proteins going to have a lot of steps, but is this because it makes a second one that's relatively inactive because it's trying to make sure that it's low enough to start all the rest of it? Or why does ACE have to come into play? Why wouldn't it just convert it?
Well, I guess, I don't know.
Okay, just
it must be some, what you're saying does make sense, and so that's probably why, but, I haven't heard an explanation for it.
Right? Because it's already there. ACE is
Well,
just
I guess,
on
we say,
the
why doesn't this just convert it to the Ang2, or, the active form? Why do we have this intermediate step? And I don't know if it's just another control step or what. I actually just don't know. Any question about this? This is the essay question. Because I want you to understand the system. Again, that's it.
So get rid of cardiovascular.
Yeah, you don't have to put cardiovascular. You don't even have to put thirst, okay? Because I just care about it's affecting these guys right here. But remember who makes it. If you forget the hypothalamus or to write that down, that's like a point off. You know, you're gonna lose these little points. So, because again, I'm telling you the question. So again, I always want that. You know, you've got to tell me who makes everything. It's really just if you just write that chart. But you know, so I'm going to be somewhere in the question I say show you how that restores, you know, blood pressure. You've got to put these guys here. Don't just put increased vasopressin ADH. Put under it increased water reabsorption. Okay, because I know that's actually, you know what it does. For this one, don't, you know, put increased sodium reabsorption and water reabsorption. Although I probably won't take much off of that. But I want you to realize, you know, what this means to us and why we're doing it. I don't care whether you put vasopressin or ADH. Okay, that's up to you. Unfortunately, both, you know, they both mean the same thing. You get to remember. I mean, this is, you know, we have like, it's a trilogy, okay? This is the first one of the trilogy, after what we've done so far. I mean, I don't mean to diminish this, because this is pretty big stuff. And what we've done, we'll take a couple minutes to breathe, and then we'll take a few minutes to breathe. And then, you know, we're going to do the last big thing before the integration. And so you'll get at least a preview of pH, because pH is going to be important. So when it comes down to it too, you know, maybe then another 45 minutes or something to complete the whole thing. So, you know, you can get a lot out, so you can be out by, you know, then I'll stay and do anything else as well. But again, if you have to leave at that point, don't worry too much. You know, try to come in early, try to look at the stuff, and I'll do whatever you're missing right now, the very beginning of class. But it would be nice if you can stay. Okay, so I need to take a drink. And
How long of a break are you?
so take 5 minutes to really regroup and do it. Take 5 minutes, and then I'm going to continue. Again, the major thing left is pH, and then integration. But pH is the major thing that if you can get through pH, you'll start to understand integration.
I'm just really excited about the kidney today.
What's that?
I said sorry to be so inquisitive. I said I'm just very excited about the kidney today.
No, all questions you're asking are great questions. So they're right on. You know, people are asking weird questions that sort of bothers me, but your questions are right on.
What goes after the NA plus?
Just that, you know, that water follows, so H2O is reabsorbed too.
So is that where it stops, or do it
Yeah.
continue going?
No. Yeah, that's it.
So can I draw it like this?
Pretty much. Liver makes that. Trigger, granules, kidney make rennet, converts Ang1, ACE makes Ang2, hypothalamus, you just put increased water reabsorption here.
Okay, underneath
There. And then, yeah, that's it. And even if you didn't, I'd probably give you 12 credit. Yeah, that's it. Oh, yeah. Don't forget, if you are leaving, turn in your thing, your test and your,
Could you go back to the very first beginning of the slide, talking about integration of the system?
oh, well, we're gonna do that. We're gonna do that next.
But I just want to copy down the slide. What on the slide? The very beginning, I think.
I know, but I put
That
it here
one,
too.
that one. Okay. Can I copy that?
Or actually, I think the better one was at the beginning.
Yeah, it's more detailed. I think.
Okay.
So nervous. So excited for
Fun, isn't it? I know. This is just. I wait all semester for this day. All semester, okay?
Do those cells that are most sensitive to the ADH hormones? Because I know these two
No, these are just cells of the collecting duct, and they're just different sensitivity to them.
Or did I put them in my bag? I have them in mine.
So you're having fun with UCSD and this past now, I guess. I can't be with UCSD that starts and then all of a sudden now it's like,
I'm in like constant never do anything.
this is true. But Christmas is coming. Like a month from now, it's like, well, I don't know when you went. You went before probably for UCSD, right? When's your last date for water?
Well, I have 2 finals on that Tuesday, then this one on Wednesday, and then one on Thursday.
Okay, pretty easy.
Yeah, so easy.
Yeah.
Oh, sorry.
Yes.
Okay.
Yes.
Hey, you emailed me the thing, but I never printed it out. Did I need to print it out?
No,
I
it's
just did
okay.
it on my
I'm making sure that machines are going to pick up my ugly
It's beautiful.
I know, you like it a lot, it's great.
Wait, I'm sorry, what did you say?
Do you think the machine will pick up all these little marks? I'm a little nervous.
It should, and if not, you can check. You can come back and check that I pick it up. If it doesn't, that in case it doesn't and I forget, just check. Next week. That's the thing that controls moving the slides and also the thing. It's like expensive. It's like $100 or something for this thing, but it's like I really need it. I've already dropped it. I've got to take up and stuff.
That looks like it belongs in space or something.
It's cool.
Like NASA makes it.
Yeah, and I broke it. What? That slide? What happened to it? Okay, guys, for those remaining, let's get ready for.
I hope so. I can't like, do you know what that looks like?
Okay, so everybody, listen up because we're about to add everything up here. Let's actually get to. So everybody, quiet down, quiet down, quiet down. Everybody, get ready, get ready, get ready. Okay. Now, actually, let me actually slow the slide and we'll get to the thing. What we're going to do now is basically start to combine everything. Sort of one step and then the other step. I'm going to actually skip one thing and go back to it later or next time because I don't want to complicate it because we can really make it in just a two-step process. So remember I said we're going to integrate all this stuff. Well, the thing we haven't talked about are these two things, which is acid-base balance. But we've talked about it before in the respiratory system when we did this. Does everybody remember this equation? Carbon dioxide plus water, and that enzyme carbonic anhydrase, hydrogen ion plus bicarbonate. Okay? And we played law of mass action, and the idea of this was, if you did it, we can do one, we had this idea that if respiratory caused it, okay, it's called respiratory alkalosis, and of course we said what? The kidney response. Let's actually do one, and we'll see it. Okay, so try to remember. Let's say we hypoventilate, because we want to get our feet wet. Okay, so we hypoventilated. So what did that do to us as far as this equation? What's the first thing that happens? We're keeping CO2 in. So you increase CO2. And again, if you increase CO2, the law of mass action said, if we have too much, it goes. And then we said, what is it? Later we're going to talk about this, but what do we say hydrogen happens then? And if hydrogen increases, pH goes down, and we call this condition respiratory. The respiratory calls it acidosis. And then we said, at the beginning, kidney responds. Well, guess what? It's time for the kidney to respond. And that's where you're going to see in a minute, this figure, this should have its own page, and I'm going to show you why. That we're going to start filling this in. Don't worry about it yet. But we're going to show you how the kidney responds to acidosis or alkalosis. Okay? But first of all, I put this one slide up that I show for even my non-majors, because if you just want to get an overview first, which is what I want, let me just kind of put. Looks like bad, but it's not. You can take all these slides. Okay. So, I mean, this is sort of an easy slide. But the idea of this is the following. Just to get it basic here. Let me just draw like I did for, like I've done for most homeostatic mechanisms. And now we're talking about pH. And the key is all I want us to do on this thing is to basically go, what the respiratory system is going to do and what the kidney is going to do without getting the specific. If our pH drops for whatever reason, we call this acidosis, which means what? We have a lot of hydrogen. Okay? 1, 2. The respiratory system, what's it going to do? Increase or decrease respiration? You're blowing out acid. It increases respiration. Okay? Your kidney. Right now your kidneys, we're going to make it easy. Your kidney's going to do one thing. It's going to conserve acid or it's going to get rid of it and excrete it into your urine. Okay? It's going to excrete acid. I'm going to show you how, right? But it's excrete the hydrogen. And again, the easy way to remember this, like for even my non-majors, you've got acid, you breathe it out and you piss it out. Okay, it's that simple, right? That's what's literally going to happen. If you have acidosis, you're going to increase respiration and breathe it out, and if you take the pH of your urine, you're going to actually have more acid there. Your body, remember, 60 times a day your blood supply is doing it. Too much acid, we're throwing that in the toilet. Okay? Obviously, alkalosis, it's the opposite. The respiratory, you're going to, if you don't have enough acid, think of holding your breath, you decrease respiration to keep it, and you're going to, in this case we'll say conserve, but we know it's going to be reabsorbing in it. We're going to conserve hydrogen. But this is the easy one. Okay? That's what I'm talking about. I love when people actually get the pizza, okay? And you can pass it around. All right, so that's pretty easy, right? So the key is, where does the kidney do this and how? Okay? And here's how. This is pretty important here. We're gonna make this slide in a minute. All that doesn't really mean anything. I should just take those out. First of all, some crazy things with pH balance happens in the proximal tubule. Yeah, we're gonna skip that. What we care about is this. So, in the distal tubule, the same place we have those principal cells, we have cells called intercalated cells. I'm going to draw them right. I'm going to make this simplified picture here. Intercalated cells. So these cells, okay, they kind of show it, are kind of, up here, the top of the collecting duct, kind of in the same, near the same area as the principal cells. But these guys are meant to respond to pH. And there are two types, type A and type B. Okay? And we're going to make this picture simplified from that. The key with this is type A, this is type B. Guess what they both have inside? Carbonic anhydrase and, that equation basically. The key with this is, remember this, type A responds to acidosis. Okay, type A responds to acidosis. So obviously type B respond to alkalosis. The key with this is now, if you look at this, we're looking at the products here. What's going to happen here, and that's why I draw the orientation here. One of these products for both of these, one's going to be reabsorbed and one's going to be secreted and basically gotten rid of. And it's going to make common sense. If we're responding to acidosis, which means we have too much acid here, right? That's what acidosis means, too much hydrogen. What are we going to secrete and get rid of? You have these two. We're on these products. Which one? Well, first of all, you have acidosis. Right. We'll just put that. And now you're basically thinking what cell responds, and you are type A, right? Because we said it. Okay, and we'll see how. So type A respond, and if you have acidosis, remember, we're going to do one of these products goes one way, one goes the other. And it would be the opposite here. So these cells are responding. If you have acidosis, are you going to reabsorb hydrogen or are you going to get rid of it? Right? We've got too much of it. So we're going to reabsorb the bicarbonate. And that makes sense, right? You had too much acid. Basically, this type A will respond. It will, And again, we can kind of put type A respond, and we'll put, whether secrete is going into the lumen, at that point it gets excreted, right? So sometimes I use, I don't care which time, it's not an essay, but type A are going, just remember, we're going to, secrete or excrete the hydrogen, and we're going to, I can't spell reabsorb all the time, we're going to reabsorb into the body the bicarbonate. So to basically try to reverse the condition of acidosis. If you have alkalosis, what cells respond? Type B. So alkalosis is you don't have enough hydrogen. So what's going to happen here? We're going to reabsorb hydrogen and get rid of bicarbonate. And right now, it's that simple. Okay? We're not going to care about the proximal tubular stuff. We're saying this is like the fine-tuning thing right around this area here. They have type A and type B cells sort of intercalated there. Type A responds to acidosis, type B responds to alkalosis, and really that's why we'll keep seeing this. We saw this in respiration. That equation and enzyme is so important because CO2 and hydrogen acidity go together. So these are in these kidney cells. One gets reabsorbed, one gets secreted, and to us it should make sense that when you have too much acidosis, we get rid of the acid, we'll reabsorb the bicarbonate. If you don't have enough, so you have alkalosis, type B respond by putting it back in the body and then just getting rid of the bicarbonate because you have to go one way or the other. That makes total sense, right? Or does it? Yes. Say that first part. These are up here. They're not responding to ADH. Okay, so the very collecting dump, they're literally where is this? So, basically, as the level, as the pH are going through here, this is the lumen, as it's passing over, that's what's going to trigger it. Okay? So, if it's going through it and has too much hydrogen, it's going to trigger the cell to basically get rid of the hydrogen. So, it's the actual pH of the filtrate as it passes those cells that would trigger these cells. So we're not talking about the hormone triggering this. Now we're actually just talking about just the filtrate passing these cells. If it's too acidic or too basic, will trigger one of these cells to start. Did I answer your question? Okay. Yes. Yes. We're gonna integrate in a minute, but right now these cells are responding to acidosis alkalosis. That's why in this case we hypoventilated. The CO2 went up, long mass action, hydrogen went up. The kidney responds. Well, actually, who responds? Type A or type B? A, right? We have created. This is respiratory acidosis. So before we stop there, the kidney responds, but who responds? Type A. What does it do? Gets rid of the hydrogen, reabsorbs bicarbonate. We finished that piece of the puzzle that we gave at the beginning. We just said kidney responds. And what did I say? Wait till later. Because I'm always thinking of this day. Okay? Every semester I'm thinking of this day. I get through it 3 times. I got 3 classes, right? And so, and we're not even to the finale. You know how some sequels aren't as good? This third part, the integration of system, is actually worth it. Okay? It's like the last episode of Breaking Bad. It was actually worth it. Okay? Okay? Okay, so, and I'm skipping one part right now that we'll come back to, that we'll need to know, but we can integrate systems now, but to do it, we've got respiratory, right, and we've got pH, we've done blood pressure, but we need potassium. And guess what? These are complicated figures. This is what you're going to draw on your test to relate to potassium. So get rid of this. I don't care about that. Because you see how complicated that was? It's really just this. But, and again, I'm going to put, why I put this cell is, this is going to be the principal cell. This is what you want on your paper. You're going to see, we're going to integrate with this.
Is this the one that's on the top of the connecting duct?
Yeah. And so all these cells are kind of in the same area, right? The intercalated cells and the principal cells, and I probably erased it. The principal cells, again, respond to ADH. I'm sorry, aldosterone. ALD. And remember, when we said that aldosterone hit these principal cells, we said it reabsorbed sodium.
And water.
And of course, H2O follows. Okay? Now the reason I have those 3 is, remember I said potassium. All 3 are those cells are involved in potassium balance. And here is how. This is to do what we're going to do next, this is the figure you write on your test to actually be able to do it. Because I've got to put potassium in here. And where it is on these cells, potassium goes where the bicarbonate goes. And it helps because there's like that negative positive. So for type A cells, when it's reabsorbing bicarbonate, it's also reabsorbing potassium. What happens if you have too much potassium? What do we call that? Hyperkalemia. We'll write this. Hyperkalemia. That's back from the beginning. Okay, these cells, as they're responding to alkalosis, are also secreting potassium. Potassium on these cells go where the bicarbonate goes. Okay? And these cells not only respond to acid-base, they're responding to, do we have enough potassium or not? Okay? If we don't have enough potassium, these guys are going to be activated to reabsorb potassium, and we're going to get to that. So potassium is involved in these 2. Now, why did I draw this? If you go back to that aldosterone picture, while we're doing this, I just got rid of it. While we're reabsorbing sodium, guess what we're getting rid of? Potassium. So these cells are involved in 2 different functions. And we're going to show you how, while it's reacting to one, it might affect the other. But to do what we're going to do, which is the integration, you basically have to, or what I do when I'm doing it, is I draw this on a piece of paper, and I'm referring to this, to do this we're about to do. Okay? Without this, I can't do this in my mind. Okay, maybe after 100 times I can, but I can't. And you'll see why. So literally, you don't even really have to put the equation in here. You just have to know what's going. You've got to know type A, you're responding to acidosis. It's reabsorbing bicarbonate and potassium, getting rid of hydrogen. Type B, you're responding to alkalosis, so it's reabsorbing hydrogen, but getting rid of potassium bicarbonate. And for this one, this is responding to aldosterone. Sodium is getting reabsorbed, potassium gets excreted. That's the key. Okay? Now, here's how we play the game. Again, all this idea. By the way, I'm going to go to this, probably not tonight, unless we stay, because I want to skip it. But what this is going to show is, and I don't want to do it tonight, or now, is that when you really, remember I said you can actually take patients, sort of, monitor these things and diagnose, that actually what you do, and we'll show this again next time, that if you take CO2 levels, hydrogen levels, and what I didn't talk about before, bicarbonate levels, you can actually diagnose whether it's respiratory or metabolic acidosis or alkalosis. But I'm not going to do this now, because that's, it doesn't, we'll do that after, because you don't need this for what we're going to do. We're going to do the integration of systems. Okay? And here's how we're going to do it. The key is we need this. And then what we're going to do is involve all four of these, and I don't care where we're starting, we're going to be able to do it. We're going to have something with the respiratory system. We're going to have something with pH balance. We're going to have something with potassium levels. And something with blood pressure. Okay? And what we're going to see is, you can start with any of these, and we're going to tell you what happens on the other. And we can go high-low, hyper-hypo, anything you want, acidosis, alkalosis. And so you're going to see by using this how you're going to sort of have every system and understand it. Every one of them. All four of these. So what do you want to start with? Give me anything.
Like cause?
Yeah, it could be high, high or low respiration, high or low pH, high or low potassium, high or low blood pressure. Hyper? Okay. Ooh, is that a good one to start with? Ooh, that'll be fun.
No.
Okay, well, okay. Let's put hyper here. Okay? That'll be the second one we do. The first one, let me actually do one. Let's do low blood pressure, because we've been doing low blood pressure, right? Now watch what some of the symptomology of when that could happen with low blood pressure. Okay? And in fact, we'll put low blood pressure. Well, I'll just do it that way. Okay, so the key way to do this, you go a step at a time. Okay, you're going to go what response to that. What we're going to see is there's going to be response, but something else might happen. If we have low blood pressure, okay, we're not talking about ADH. We're talking about these guys. Okay, if we have low blood pressure, which cell is going to be activated here with these? Okay, these are involved in pH right now. Principal cells, right? Because I already erased that thing. If we have low blood pressure, what's going to happen to aldosterone levels?
They're going to
Increase. Okay, so it's affecting this. So that's what I want to put on here. For low blood pressure, we're going to have an increase in aldosterone. Everybody agree with that? Because that was on our other chart. We saw how. Okay, now, and that's right what happens. If we're doing that, we are reabsorbing what? And that's helping us restore blood pressure. Everybody agree?
Mm-hmm.
But what else are we doing?
Releasing potassium.
Potassium. We're getting rid of potassium. So we're excreting potassium. And if you think about it, remember, this is like going back and forth. If we excrete too much potassium in this response, what condition are we going to have? Hypokalemia. We've lost potassium. Before I go on, does everybody follow? If you start with low blood pressure, you're looking over here. These are the only cell we're talking about that's responding to blood pressure. Okay, and when we already had it, that low blood pressure, aldosterone is going to increase so that this would happen. Sodium gets reabsorbed in water, that restores blood pressure, but this also controls potassium. We are losing potassium. And so you might have the condition of, in this response, having hypokalemia.
So low blood pressure, it makes the principal cell respond.
Because low blood pressure, by that pathway, triggers aldosterone, and aldosterone makes the principal cells respond. Okay. Does everybody get it where we are so far? Now, the next thing you say is, whenever we're doing potassium, the following is going to happen. We'll just see different directions. We're going to involve this guy, no matter what. Right now, we're already involved in. And one only of these. So you don't involve both of these. You're only going to involve one of the intercalated cells because they're responding to potassium, and it's going to be the most obvious one. If we have hypokalemia, okay, basically, we want what? Do we want potassium reabsorbed or getting rid of? So which one does that? So this is the key. Type A are going to respond to the hypokalemia. So type A respond, and then you just look what they do. They're going to reabsorb potassium to correct that problem, but also, and reabsorb bicarbonate. But what are we getting rid of? Hydrogen. Okay? If we're getting rid of hydrogen, what condition might we have? If we get rid of too much hydrogen? Alkalosis. You're right. And what kind of alkalosis? This would be metabolic. So by the type A responding, we reabsorb potassium to correct that, but we excrete the hydrogen, and that means we've lost it. We have caused potentially metabolic acidosis. Okay? So let's and we're going to repeat this, and we have one more thing to go too. But let's follow this again. You start with low blood pressure this time. So you know this is the cell that's involved. These aren't involved right now. You want to restore blood pressure. Aldosterone goes up, so we reabsorb the sodium water to take care of that problem, right? But we've gotten rid of potassium. That means we potentially have hypokalemia. Okay? Now the idea is these cells are going to respond to hypo or hyperkalemia to try to correct it. If we don't have enough potassium, this is going to be stimulated to reabsorb potassium to correct it. But now we're also losing hydrogen, and that's causing metabolic acidosis. Do we have another system that we haven't covered? Is there something else that's going to respond to the acidosis? Respiration. What are we going to do with that acid? So we increase respiration. Okay? Blood pressure at the beginning. Potassium. pH. Respiration. We've involved all of them. By the way, once you involve all of them once, you stop. Because some people come up, well then, so what's going to happen? And it's true in real life. That's why, and we'll do this. This is why this is so beautiful. Because especially if you're going into healthcare and all that, you got a patient coming with all these different symptomology, and you're like, is that the cause or is that an effect? And you can start to piece it out of why. Because in fact, I'll put this up here, and you can kind of go back I'll do it in a way. But the idea is, and when you give an ACE inhibitor, does anybody know what you give it for? Okay, what do you treat? Why would you give someone an ACE inhibitor?
To activate the Ang2.
To inhibit it. If you have high blood pressure, what do you want to do?
Oh,
Lower blood pressure. Okay? Let's actually look at this second, because I want to actually show you, fit this in. Yes?
I think that you made a mistake with the metabolic acidosis. I believe it's alkalosis.
Oh, did I put that?
Yeah.
We've lost acid. Sorry. Thank you.
You said that.
I just don't see.
Thank you.
That'll decrease. Okay.
And decrease respiration. Change that. Thank you, back row.
All right.
See, sometimes the back row is paying attention, okay? Actually, everybody here, you are the winners, as you can tell. You've stuck it out, and this is all, you can tell, again, this is a money-back guarantee, that this is going to make sense to everybody, especially if you draw it right, okay? I want to show, let's show let's show this again. So just because I'm going to add something to that, and we'll do another one. The idea is, look, if you had low blood pressure, you do all this, including ACE, to increase these things to raise blood pressure. Now, what if you have chronic high blood pressure? You want to reverse that, right? If you have high blood pressure, you want to lower it. So do you want ADH and aldosterone? No. And so an ACE inhibitor, by inhibiting this, you inhibit all of this. Okay? And so really, if you look at this, we could do it that way, but if you gave someone an ACE inhibitor, okay, it would do all this to try to lower blood pressure, right? Okay, an ACE inhibitor will do that. And the key is, if you follow this, which we did from low blood pressure, if you go online and you look at ACE inhibitors and you look at counterindications or things you need to look for in patients, guess what you're going to see? Hypokalemia, metabolic alkalosis. Okay, these are side effects that if you went too far, and you're lowering your blood pressure, again, just like with the cardio, these kidney systems are going to try to counteract, and you can potentially have these conditions because of what we just did. So again, instead of memorizing, these things you need to look for from these drug reactions, you're going to understand why it says you're looking for hypokalemia and metabolic alkalosis. Because all these other systems are responding to the fact that you lowered blood pressure, okay, and they're trying to counteract it. But as they're doing, since we have cells doing more things than once, you have something happening, and then it says, okay, I'll take over, and then you have that, okay. And that's why, if you come with the patient, they have hypokalemia, you don't know, was that, is something else causing that, or was that an effect from the drug? You've got to get all this information to actually piece it together. Hyperkalemia? Sure. Like I say, and you're not going to memorize, don't make 8 note cards, okay, of all this. Practice doing this. This is the key figure. You could start with any of these, okay, any of them. And we just started with low blood pressure. You could do high blood pressure. But let's start with another one, and we'll do the one that he said. Let's try hyperkalemia. So hyperkalemia is too much potassium. The reason I did this second, because we're going to sort of branch here. Now, I want to say this as I'm doing this. The last page of the extra questions, actually the last 2 pages deal with this. What we're doing here, it's not going to be an essay question. I'm not going to make you do it that way, even though I have you practice. It's going to be a series of multiple choice questions that I'll basically taking you in this condition. Aldosterone goes up or down, or something like that. And then, as a response to that, it's hypokalemia, what response? Type A, type B. I'm going to sort of, the multiple choice questions will take you through this. So that if you get this and you're drawing on the side, you get like 10 points. If you don't get it, you've got that random type thing going on. So it's these questions will be multiple choice so that, it will help guide you on where to go. But again, I would probably do it this way so you have their answers right next to it. So hyperkalemia, the reason it's going to branch is when you're talking about potassium, you're looking at this thing you drew like 1,000 times running your test. You're like, hey, these cells respond to potassium, and these cells respond to potassium, right? So we're going to do one of these and one of these. If we have hyperkalemia, let's go over here first. That means we have too much or too little.
Too much.
Too much. So what do we want to do? So who's going to react here?
Type B.
Okay. Do you see how beautiful this is? Okay, this is crazy complicated. You tell anybody about this, they're like, oh my God, and you all get this. This is the money back guarantee. You look at this. You have type B respond. I love this part, okay? Type B respond, and you just see what they do. They're going to excrete or secrete, I don't care, the potassium to take care of that. Okay, to correct that. But what else are they doing? And reabsorbing. Again, you can put both. But right now, look, you're reabsorbing hydrogen. And creating?
Acidosis.
And what kind? Metabolic. Okay, now let's make sure I write it right. So this could create metabolic acidosis. Is there any other system of our body that's going to respond to acidosis? And respiration is going to?
Low.
We breathe out acid. Increase respiration. We're done with that column. But over here, who else responds? Because remember, you only have one intercalated cell and we're done. Okay, so you don't have both. Okay, but who's over here? We've got the principal cell, and the key with this now is, again, we're dealing with hyperkalemia. So, and I should say this as well. So besides the fact that you only use this, you've got to think of the following on this. That, again, these are responding to aldosterone, right? If you increase aldosterone, you reabsorb sodium, and you're getting rid of potassium. What you've got to realize is, if I have it where you're inhibiting or you're decreasing aldosterone, the way to do this is to reverse it. It's not like they reverse, but you got to remember, we're in like a normal balance here. Like we're secreting, like if these are working, we're secreting the right amount of potassium. If we decrease it, all of a sudden we're accumulating it. So to do it on this way to understand, and we'll do one of those, you got to remember, anytime that we're reducing aldosterone, then we are going to be reabsorbing potassium and getting rid of sodium. Okay, and I'll use that next. But right now, I don't think that's going to be the case. Because, again, we are responding to hyperkalemia, which means what? Do we want to keep potassium or get rid of it?
Get rid of it.
So we're going to increase aldosterone. Because that helps us, right? So we're going to then get rid of, I'll just put that first, we're going to excrete the potassium to correct that problem, right? We had hyperkalemia, we excreted. But what are we also doing? Reabsorbing salt. No, we're reabsorbing. That's why I always follow this. And water. And that can cause what? We're reabsorbing salt and water. Increased blood pressure. Right? More water and salt, more volume, increased blood pressure. We've involved, and we'll do a couple more of these. We've involved potassium. We started that time. We've involved acid base. We've involved respiratory system. We've involved blood pressure. Do you see how that's the key? Okay? If you don't draw this on and start playing with it, if you're doing it in your head or something, it really doesn't make sense. If you start with potassium, it's branched because this responds to potassium and one of these respond. If you start with acidosis, this is going to respond, but it's going to create this and this. So we have to just play with this. Let's do the following.
You say acid base, you're referring to potassium.
No, acid base is alkalosis acidosis. Potassium level is hyper or hypokalemia. Let's start with. Okay, hang on a second, because I want something to happen here. We're going to have that happen, and then that means that happens, and so we want that.
You're doing it in your head.
Yeah, I am a little bit. Okay, let's vomit. Everybody, no, okay. So we're gonna vomit. Okay. Let's go back over here, back to the old days. Okay, let's put our figure back here. Because we did that back at the beginning. So if we vomit, we are losing what?
Hydrogen.
We're losing hydrogen, okay, which means pH is going up. And what do we have? What do we call that? Metabolic alkalosis. Okay? Let me put it here. Metabolic alkalosis. I agree. That's back from the early days. Okay? Okay. So we have two systems to respond to that, right? We have what? Respiratory kitty. Let's get respiratory out of the way. If you have alkalosis, respiration is going to decrease, and we're done. That's a nice column there, right? Okay, because now we got the respiratory done. You decrease respiration, hold in the CO2 to restore. Okay, but the kidney responds too. So you go over here. Which cell is going to respond directly to the alkalosis? Type B, because type A responds acid. So again, you look at that, you say you realize type B responds, and that means it's going to reabsorb hydrogen to correct the alkalosis. But it's doing what? It's secreting bicarbonate and potassium, which may cause hypokalemia. If you're losing potassium, that's hypokalemia. So you responded to the alkalosis by reabsorbing hydrogen. Yay. But you're getting rid of potassium. Maybe not so good. Okay, maybe everything's cool. Maybe you've done the right amount and you go home. But the key is, sometimes if you're responding, the idea is this is happening. Now you potentially have hypokalemia. Is there another cell type that you drew, besides the intercalated cell, that is going to respond to potassium levels? Principal cells. See why this is the key figure. And so we're going to have that, and the key with this now is that we don't have enough potassium. So do we want more aldosterone or do we want less? Ah, see? Because if we had more, we'd lose more potassium. So we tweak it down. So the principal cells respond by losing or decreasing aldosterone. So again, you've got to remember, you kind of reverse it. So now you're going to what? Reabsorb what? No, this is why you go slowly here. When you decrease it, you reverse these. So you're going to reabsorb potassium. Okay? So now, remember, this is when we increase it. This is how it normally works. If we're decreasing it, you switch these. So that means, in this case, that's why we decrease it. We want to reabsorb. We don't want to lose the potassium we were losing before. We want to basically keep it. And so you basically have this idea by lowering aldosterone, we reabsorb, or lose less, but right now it's easy to say reabsorb, potassium to correct that condition. But what are we getting rid of? So we excrete sodium and water, and what can result from that? Low BP, and also I'm going to put, by the way, since we did it, high urine output. Because that actually is part of how a diuretic works. Okay? So, do you see what we did? This time we started with a pH problem, metabolic alkalosis. We got the respiratory system done. Check. Some people say they're going to put those up there. We've got the intercalated cells responding to it for pH. Check. We've got potassium. We respond to that. And we've got blood pressure. So, again, I don't know if I still have them up here. Now we've started, we did one with blood pressure. We did one starting with potassium. We did one starting with pH. And we can do one starting with hypo or hyperventilation. Okay? Does everyone see? You're not memorizing this. You're practicing this. Okay? The key to practice it is do one step at a time. Okay? Because otherwise you can get lost. And use this figure. You have to know this figure to be able to do it. Either in your head, or I can't do it in my head. I mean, a little now I can start, but if I haven't done it in 2 months, I draw this on and I make sure I can do it. Okay? So, but that's the key. We can do another one, but that's sort of the main thing.
Can you put an extra piece of scratch paper on our exams?
Yeah, I was kind of wondering that too.
Yeah.
It's hard to-
I mean, yeah, I'll try. I'll do it. We just have to make sure that that you basically write your name on it and turn it in. You can't because some people can take it away. I worry about people taking away my questions because you reuse questions and stuff. And not that 99.9% of people are honest, but some aren't. So I'm a little weary on handing out extra pieces of paper. But because I love you guys and I wanted you all to do better on this test and not hate me as much. But the thing is, you guys get this. I already know that. No matter how you do on the test, everyone gets this, and it's really cool. But yeah, so we'll have a piece of scratch paper so you can actually have that on the side instead of having to turn pages and stuff. Because clearly, you need this, and again, it's got to be my scratch paper, so don't come in with one, because then that's like notes. But it needs to be this and probably that low and high blood pressure one, or whatever you want to, start to draw on it right away. That's fine. So yes.
Is Monday only the review, or are we going over new material?
The only new material is, and again, I can also do this after this and people that want to stay. I just want to make sure we got the 99% of it, is to go back to that slide that I showed, that's only on your PowerPoint and not on your handout, to explain how to do this. Because again, I don't like memorizing, that type of thing. You could memorize this, but I can actually help you go through it so you actually understand that. But that's the only thing that I'm not, I've covered if you want. After we'll finish. We'll just do a couple more because this is it. This is the only other thing that we have to go over. But this is it as far as the integration of systems. Okay, except just playing it with and making sure you get it. Do you want to do a respiratory one?
Yeah.
Sure. Okay. So that again, we're doing probably 4 out of the 8 right now, but you're not memorizing these. It doesn't make any sense to memorize them. So let's.
Is the kidney exam our last exam?
No.
Oh.
But it's our last real fun. Okay. Now we have again our last scheduled exam that everyone has to take is going to be on that Wednesday, not the following Monday, although that's the last day of school. The Wednesday, whatever that is, the 13th, I don't know what it is. That's test 5. And everybody needs to take test 5, which will just be on this last section, which will start after Thanksgiving. Okay?
Oh, okay.
Now, the Monday, and I won't even be here because I'm going to be in Hawaii. The Monday is, but I'll have, no, not Stu. Who's going to do it? Susie. Okay? Anyway, it's going to be for people, and we'll know by then, the cumulative makeup final, which covers the first 4 tests. And it's all multiple choice. And you'll know going by the weekend, since I'm going to have mostly, if not all of those test 5 multiple choice, run the Scantrons, put the scores in. You'll see, if you even need to take it or if it's worth taking it. If you need 102 on it to move up a grade, probably not worth taking it. But if you need 10, 15 more points than you had on a low test, maybe you'll take it. It can't lower your grade, but it's stupid to take it unless it's actually going to help. And you'll know. You'll know if you don't take it what your grade is. So then that Monday you'll take that. Otherwise, you don't come in. You're done that Wednesday. You don't have to come in that Monday. Again, I won't be here that Monday because I'm having a sub and I'm actually, off to Hawaii. Okay. So it's cool because my son's like 24, but he actually wants to take vacation with us. So it's him and his girlfriend and my wife and I. It's going to be like a fun little trip. Maybe I'll learn how to surf. I might drown. So.
I thought you were a surfer when you first came in.
I just drown. My son though is the master surfer, but he's not genetically my son. That's why he's got all that talent. Because if I go, I'll have to take a picture. Too bad I don't have Facebook because you can see me like drowning or something like that. But,
when we're taking all these supplements, whether it's like blockers and inhibitors, does it all have to do with the proteins? Because that was crazy where you're talking about in the kidney that there's certain diuretics that work, whether it's in the ascending or distal or even collecting gut based on what the proteins are in the cells.
Yeah, it's because these are when we're talking about the proteins. Even when we're showing that, those are like embedded. Those are the transport proteins, right? And so you're basically either inhibiting them or actually, most of the time you're inhibiting them. You're making them not function quite as well.
Yeah, it's just amazing. I mean, we know so much nowadays, and you actually learn how it works.
Right. Well, that's the thing. Everybody knows diuretics, and now that you actually see the mechanism, and it's all involved in the party, right? Same thing with diabetes. What do we know? Sugar goes in the urine. Why is there frequent urination? Because water follows the sugar. Okay? Too much sugar stays there, water follows it, excessive urination and thirst. That's why that makes sense too. And now you understand why diuretics. You have to admit, okay, we'll do one more. You have to admit this is a pretty good sequel. Okay? Everyone here understands this, okay? Maybe you're not ready to go out and sell it, but everyone I can do this, okay? And I just otherwise I got to give your money back.
So is that the movie?
This is the movie.
Oh, okay.
Okay. Okay. Well, no one's died yet, but I mean it's not that good, but it's still. And we do more ones, yeah.
When we're talking about, so when you stopped right here for type B and the respiration, even though when you're increasing respiration, you're getting rid of more hydrogen. What did you say about these cells? Like, how would you not think to go back to one of these and say, reabsorb?
Because, once you involve one, you're done. Once you.
Okay.
What I mean, as far as in other words, and then you got once you've involved one each time, you're done. It's it's possible then the other ones, eventually everything might react, but you already had type B respond to the hyperkalemia, right? To correct that. Okay, so you've increased.
So it's not going back to type B. Oh, I see, because they would just be going in loop.
Yeah, exactly.
Okay.
And right. I mean, maybe things will eventually go into loops, but we're not looping out, right?
Right. So like they're usually involved. So okay, that makes sense.
So as long as you involve one of everything, you know you've done it right. You can even check it. So, are we hypo or hyperventilating? Do one of those?
Hyper.
Sure. So we hyperventilate, and what are we doing? We're lowering. We're getting rid of CO2. Da da da. We end up lowering without even going through all the steps. We lower hydrogen levels. Yeah. So pH is going up, and we call this condition respiratory. Calls it respiratory alkalosis. Okay, that's old school, right? We did that in the first 2-3 weeks. Again, we hyperventilated. That means we've lost CO2. We're losing hydrogen. We have respiratory system cause it. It's respiratory alkalosis. So, respiratory is done. Okay, this time we started. So what's our next step?
Then we see which one of the cells are going to respond.
And who is going to respond?
Type B.
Type B respond. Okay? So type B respond, and so we write that. Because type A responds to acidosis, type B responds to alkalosis. So type B responds, and then you just write what happens. Okay? You have it right here. We're going to reabsorb hydrogen to correct that. Right? We didn't have enough, we reabsorbed it. But what are we secreting? Or getting rid of?
Potassium.
Okay, bicarbonate and potassium. And if you secrete potassium, what do we think of?
Hypokalemia.
Hypokalemia.
This is a cool movie.
This is pretty cool, okay? Now, you have hypokalemia. Is there another cell type that's going to respond? Principal cells. Do you see what I mean, guys? You see how everybody gets this? And if you tell other people, they're like, you got to be kidding. How do you know all this? And you're like, okay, I stuck through this horrible class with this guy who gives horrible tests, but then something cool happened, okay? And this is what it is. You have hypokalemia, we're going to have the principal cells, and we're talking aldosterone. If we don't have enough, we want to basically have more. What are we going to do with aldosterone if we need more? Decrease. That's the one that you got to get in your mind, okay? That if we increase it does this, we want to decrease aldosterone. Because by decreasing it, we're going to reabsorb what? To correct the problem, because we're reversing it, reabsorb potassium, but of course, what are we going to also do?
Secrete sodium.
Secrete sodium and water, and therefore lower BP / increase urine output. Booyah. Okay? And and again, you've got to practice this. You're not ready to probably take the quiz right now, right? But you get it. And not only do you get it, but I think most people are like, this is totally cool. And so, again, especially, I don't know how many people really are going into healthcare or anything like that, but you're going to understand when you're reading all these drug interactions or when you're trying to figure out what this person has, it's not that easy because you just got symptoms. You got high and low potassium or acidosis, alkalosis, or CO2 levels, and you're like, what's going on here? What's causing it? Then literally, by understanding this, it starts to make sense. Okay, you'll start to see why. And then again, you've got to be detectives and figure out what was the initial cause and then what came after versus, and that's not that easy to do. But this is putting the four systems together as one. This is why this was the key to the course. After this, last section, and not as exciting. Okay, but we deal with sex, but not that much. Okay.
For the principal cells that are going to be responding with the hyperventilation, when you get the low blood pressure, eventually, never mind, you have it. There,
Yeah,
forget
and
it.
stop. Just remember to stop. Because then people are all, well then, rent it. Well, you gotta stop somewhere, okay? For this course, we stop here. But again, you can see how things really get complicated and why every patient or whatever is going to be different. Because, what are the levels of response, that will actually occur? Yes, ma'am.
Are you just not writing the permanent down? Or
Yeah.
Okay.
And so, just because the hydrogen is sort of what I remember, but you can write again. It's not going to even be an essay, but that's why. Yeah, I mean, it is happening. I'm just not writing it down for just brevity. So again, the idea of this is when you look at the extra questions now, because you're set for the extra questions. There's only one thing I haven't done, and again, I'm going to take a few minutes for people to leave, but I'll stay, and we can go over what we didn't cover. We can go over this again. We can go back 17, 18 again. I'm always, I'm going to be here at 10 o'clock, but if people are here, both now and on Monday as well, so you can ask any questions you want. Again, basically, except for this thing right here, you have everything you need to know for the test. Again, when you look at the extra questions, the second page, I have you kind of doing this for practice, but the third page is like the test is going to be, in which you'll see I'll have a series of multiple choice questions that will basically mirror this, and you just have to go the right way, that you're knowing the right one. So it's it's a little easier or harder depending on what, but I think it's a little bit easier if you get this, okay? And I think everybody gets this. It's just practice, okay? I don't think this is like what is he talking about? I think you actually all get this. That's the key. You got to draw this figure. You can't do this in your head. At least I can't. Okay? If you have this figure and just work through it, you're going to do okay. Any questions on what we've done? Okay, so again, make sure if you leave, you turn this in. Okay, because I got to run Scantrons. Okay, I can't have it like by mail. And also, if you leave, take your recorders. So my voice is going a little bit. So what? Don't leave me alone for 5 or 6 minutes. Okay. Some people are going to come up. I mean, I'll be here, but sort of regroup yourself and let me sort of get my voice back. And I'll stay and help people whatever they want. But thanks for staying, guys. I actually really appreciate it. I love when I see this extra effort. I know you're tired and all this is going on. I'm hoping it's going to be worth it.
Oh, it better be.
But see, you're getting it.
Yeah.
Okay? Just don't go the other way fast, okay? Take your time, because you go like, yeah, and if you just look at it, you get it, you actually get it right. You get it, I know that, but just on the test, slow down a bit so you go the right direction, okay? But it's cool stuff. You have to admit. I gotta sit down and I'm tired. This is like, do you think I could do this for 20 more years until I'm dead? I mean, I'll be like 73 doing all this. Look at this. Because I can't retire, so I have to die either on my bike or in the classroom talking about the kidney. It just drop over. Those are my choices.
The guys are involved on like 5 or whatever. Yeah.
Really?
All have lots to say. Like, that was a good one.
No questions?
Oh my God.
As long as I have to talk about what?
No, usually not. So you said just go through all of them, and as long as you incorporate all 4, you can stop, right?
Right.
So that's hypercooling.
Right.
Okay. Type B.
We'll just follow it. You get rid of that, but what did you do? So that's pH.
Oh, that's pH.
Okay.
And then respiration. What about blood pressure?
Okay, we'll go to the other side of it.
Got it.
So you're always going to involve.
Oh, I did see this like last year.
You always see how you're involved, and you can see that one too, right? You started with blood pressure. You've got to potassium. You've got to acid base, and you've got to respiration. So you're always going to involve one. Sometimes you have these branch things,
Yeah,
but
it involves like 2 different ones.
Yeah.
Sometimes it takes 2 things. To,
right, because the key is both of these respond to potassium. So if something's wrong with potassium, these both respond, and that's why it branched, right? Sorry you missed choir stuff. I'm really sorry about that. You have to do well on the test and feel better.
I have to go to work tonight and spend the night over there.
so.
Well, I'm glad you
If I
stayed
want
because it
any-
really was important. You could see to
No,
do
I know.
this.
I was sitting there, I was like, do I stay for longer? So I want to stay for longer, but I have to be to work at 10, and I haven't been home since 5:30 this morning, so I want to see that man I married and those little cats.
Oh, I thought you were going to see him until Christmas. Sorry, no. Okay.
No, I don't see him, like, but, and I need some real food, because corn nuts don't count as food.
No. So just think about this, let it sink in. But I'm glad you stayed.
I know. I want to stay longer, but
Well, now it's. I mean, it could be almost overkill. I think for a lot of people. I mean, their brains are pretty full, so I don't think staying longer will.
this
will
is
really
kind of
help.
big.
This is.
I'm
the big
already.
one.
I just want to go home and like write it down
Yes.
again.
Do it as soon as you can.
Sometimes I just get confused because people ask questions
Yeah.
that confuse me more, and then I'm like, and then I'm listening to the lecture later, and I'm like, why? Like, just I wish I could cut out this whole like 5-minute.
Yeah.
So anyway,
understand.
but
That's
I know
what-
Monday's my big one. I always for the whole thing right before the test. I'm always like,
Yeah. So do as much as you can. Then Monday it should be. Make sure you see what questions you have, and then Monday would be
did
the
my
big one.
email go through over the weekend or no?
Yeah. I have so many.
That's
of those.
fine. No, I just want to make sure it goes through in case like I
Yeah.
have like a dire urgent request question like
Okay.
over this weekend or whatever. They can't wait till Monday.
Yeah.
Okay.
But
I will
say,
put read me urgent
do
desperate.
that. Do that. Because then I'll make sure I answer
Okay,
it.
thank you.
Are you gonna go over anything new?
If people want to do this, I will. So I might do it, but I'll do that at the beginning next time too. Just the one thing, and then nothing. Everybody else is just whatever people want to review.
So we're like completely done with the lab part.
Yeah,
Is that
lab is
correct?
done.
Okay. I was gonna see. Do you want my book? Because I really, because I know you were saying how yours is kind of different from that. Do you want it? Because I don't want it.
You don't want it all?
No.
You can't. Do you know a friend or something that's going to take the class?
No, I mean if you want to, maybe you can just like store it over there, and then if
Yeah.
somebody needs it, they can use it.
I can do
'cause,
that.
I mean,
Thanks, I
Yeah.
appreciate it.
I ate that much. I feel
No, I mean, you look on the picture, it's got all kinds of stuff going in, but really all I care about is that, and that. So you look at the picture, it's got all sodium, potassium, pump. It's got all this extra stuff of how it works that I don't care. So that's all you need. And even when you do this, you don't have to draw the equation really, but it helps me to do it, right? It's in my brain.
Did we not finish with a hyperventilate when you have a higher pH? Didn't we not finish the respiration part of decreasing it to hold in
No,
CO2?
No, because when it starts there,
Oh,
you
it's
don't do it
already
again.
there.
Right. So again, when you start respiration, it's done. You can take care of the beginning.
Are we starting? Or are you still having a break? No, take a break. No, I did not.
I'm the same. I wanted to ask.
No.
Ask each other for this. This is a minute or two.
We're so excited about this.
It is though. I know. That's why I lose my voice on these days. Okay.
Yeah.
I have one more question that I want to
Don't take that job.
No, we'll wait.
Yeah.
Excuse me, Professor Michael Biot.
Ask you. So
I want to
is
be sure
the-
to my
is the,
answer right now.
Is the bicarbonate level the same? You know how all through all this we're like potassium.
I don't have this one right here. So if you have a defect, you type that.